Cool. All right, slide one. So I'm excited to talk to you guys today about Numba, which is a compiler for Python functions. I put all those words in there because they're important, specifically the functions part, which I'll come to. Slide two, just a real quick update on my background. I'm actually a particle physicist by training. Did my PhD on the Sudbury Neutrino Observatory in 2008, and then worked as a postdoc for 5 years on a whole bunch of experiments. It was really sad that I left LB&E before it renamed to Dune because I wanted to get in on all those sci-fi puns that I'm sure you guys are making. Worked on some other stuff after I left physics. Worked at a vehicle tracking and routing company, and then for a little while, and then landed here at Anaconda, which was called Continuum Analytics at the time, which are the creators of the Anaconda Python/R distribution, as well as a bunch of open source projects. So we're a startup. Currently, I manage the Numba project. I'm not the lead developer. I maybe would classify myself as the lead cheerleader for Numba, plus doing some development. I also coordinate all of our other open source projects that we do here, of which there are many, and a bunch of other things because it's a startup, so there's always a million things to do. So just that background is really just to give you a sense of I spent a large chunk of my life working in root and Python and GPU stuff. So Numba was actually a fairly natural transition for me. So a lot of people ask, why would you bother with a compiler for Python? And it's really, I think, about striking a balance between productivity and performance. Python has become very popular for scientific computing. And it integrates, part of that, I think, is because Python specifically integrates very well with external C and C++ libraries and Fortran, actually. So things like MKL for linear algebra, TensorFlow root, all of these things are easy to call from Python, which makes Python a fantastic sort of glue language. But then what happens when you come to custom algorithms and other customized data processing tasks where there isn't a tool already doing exactly the thing you want to do? So our goal, as in this predates me here, but back in 2012 when Numba was actually conceived, although now I would say the current incarnation of Numba really dates back to something more like 2013, 2014, where our goal was really to make a compiler that worked within the standard Python interpreter and didn't replace it. I'll talk a little bit more about that later. Integrates tightly with NumPy because NumPy was sort of the data format, the in-memory data format for Python, for scientific computing in Python. We wanted to be compatible with multi-threaded and distributed, and ultimately, non-CPU parallel computing as well, which sets a little different set of constraints on us that you don't necessarily see with some other projects. So Numba is a JIT compiler for Python. Specifically, it's an open source function at a time compiler. So there are different approaches to this. You can imagine compilers that analyze whole programs, compilers that do what they call tracing, which is what your JavaScript browser, your JavaScript interpreter in your browser does, is it actually traces the execution through the interpreter and then eventually identifies hotspots and compiles those. That's not how Numba works. It's a compiler toolbox is actually the way I think about it. It's not a single execution model or a single target hardware. It's really a collection of related, very lightweight compilers that are designed to operate natively within your Python program. The speedups are kind of what you would expect going to machine code, anywhere from 2x compared to some basic NumPy code to 200x if you are literally writing pure Python for loops, which sometimes is the easiest way to express an algorithm, but obviously runs terribly. And so if in those situations, you can often write a much simpler function using Numba to compile that from pure Python down to machine code. Our goal, really, our gold standard is Fortran. We have a joke that Numba is actually rehashing the history of Fortran. I think we're up to Fortran 95, possibly with some bits of Fortran 2003 and later in there. But really, Fortran speeds are what we're going for. But we want to keep that with the ease and the feel like you're writing native Python and NumPy code. The compiler is BSD licensed. This has sometimes confused people because in the past, long ago, there was a Numba Pro where the GPU compiler was proprietary, but the CPU compiler wasn't. That's all gone now. It's all BSD licensed. It's just developed entirely as open source in the public. And our goal, really, where we view this tool especially having value, is for empowering scientists who make tools for other scientists and for themselves as well. Not that random end users may necessarily be sitting there using Numba, but the tools they use were built with the help of Numba. That's I think, our biggest goal. So slide 5, when you're dealing with Python compilation, there's a whole maze of trade-offs, and there's no right answer to this problem. I often get the question from people of, is Numba better than PyPy, or is Numba better than Python? And honestly, they're all addressing the problem differently, and so it helps to understand the differences between them to decide which is the most appropriate. There is not, Python is fundamentally not designed to be compiled. So any attempt to do so is going to have to deal with trade-offs, and there are different ones that are valid in different situations. So one approach, which Numba is not, is a complete replacement for the Python interpreter. There are projects like PyPy, which I think has been the most successful, Piston, which is I think basically dead now, Pigeon, which is sort of slow burn. I don't know how rapidly things are happening. If you remember Unladen Swallow from long ago, these are all attempts to basically rip out the C Python interpreter and replace it with another one that can do some kind of just-in-time compilation, often using the tracing approach that you see in your JavaScript browser. This is really hard to implement. The PyPy developers have spent a decade getting this to work, and they've done a spectacular job. I have huge respect for them. But it is also difficult, and this is something only recently I think that has been improving in PyPy, to maintain compatibility with existing compiled Python extensions. The reason we did Numba the way we did is, at the time, losing all of the compiled Python extensions like NumPy, SciPy, Pandas, AstroPy. I mean, there are all of these compiled tools out there that you would just not be able to use if you switched your interpreter out. So that's why we decided not to replace the interpreter, but to work it with it. And also, a replacement interpreter doesn't address non-CPU targets. That's fundamentally something you need a different approach for. Another approach is translation of Python to C or C++. This is like Cython, Pythran, Theano, Shedskin, Nutica. There's a whole bunch of these. It's hard and it's somewhat limiting to try and do static analysis of Python to convert it into C++. You're either stuck generating under-specialized code, both under-specialized in terms of you didn't generate the most optimal code because you didn't know exactly what data types were going to be used. You also didn't know exactly what CPU you were going to be running on, so there may be vector instructions you weren't able to take advantage of. Or the opposite extreme is that your compiled code is insanely bloated because you have to compile for every possible combination of data types, which rapidly becomes untenable. Things like NumPy don't even do this. They'll often just cast you up to generic 64-bit types often in order to not have to compile every possible permutation of data types. The final thing actually is if you do have any kind of JIT compilation approach in these systems, which several of these do that, it assumes that you have a C or C++ compiler on the target end user system, which on a for Linux users is kind of a no-brainer. Almost all of them have one. On Mac, it's a little less common, and on Windows, it's very uncommon. And asking someone to install a multi-gigabyte compiler just to be able to use your code for a lot of our users is just not tenable. So you can fit our compilation system in 100 megabytes or less, rather than the size of your typical C or C++ compiler. And I just want to emphasize that these trade-offs don't make these other approaches bad, they just make them different. They may actually be combinable at some point in the future. All right, so let's go to slide 6, basic example of what Numba looks like. Our goal with Numba is to be as minimally invasive as possible. We do require the user to opt in because we're not taking over the interpreter. We need them to tell us what function they would like us to compile, which we use the JIT decorator to do. So here's an example of a function written in kind of a Fortran-y feel where we've allocated an output array. Actually, let's go to slide 7, which notes stuff. So one of the things the decorator does is what Numba's goal is to translate the body of the function into something that has no Python types at all, no Python objects. It's all pure native numeric types or other structs and things like that. So by setting that no Python equals true option in the decorator, you're basically telling the compiler to raise an exception if this can't be achieved. If the type inference can't figure out the machine type of everything in the function, it'll raise an exception and tell you, sorry, I can't compile this. That prevents it from falling back to a less optimized mode, which is, at this stage is not super useful, but in the future maybe. But otherwise, inside this function, you can do stuff that looks like kind of normal Python. You're using the NumPy functions to create an empty array. You're looping through them using an iterator. You're doing some tests using some NumPy math functions, and you're basically removing all of the nands in an array and compacting it and reducing a subset of it. And this is a silly example, but it's to show you that the goal is to keep it fairly lightweight. And actually, in this example, it happens to run 2.7 times faster than the native NumPy. So, slide 8. So how is this actually working? So what Numba is doing when it compiles is it is waiting until call time. So if you decorate a function like doMath and then you run it, it doesn't do anything when you decorate it initially and you declare the function. But the first time you call it, it kicks off this entire compiler pipeline. So the arguments are looked, the types of the arguments are considered. In addition, the bytecode of the Python function. This is one thing, this is a subtle detail. Numba compiles Python bytecode. It doesn't compile Numba source, or it doesn't compile Python source code or abstract syntax trees or other things that people imagine. It actually is not looking at your Python source. It's looking at the bytecode that's generated when that source code is parsed and emitted, which actually allows us to compile functions you may not have the source code for, which can occur in a number of reasons, a number of situations. Regardless, that bytecode is analyzed and converted to a different internal representation and combined with the function arguments to do type inference. This is where the magic happens, and we go through the function, we figure out, is this variable a float? Is it an array of floats? How big are the floats? All of these things are done. Then there's some rewriting passes where we can do optimizations that I'll talk about later. And then lowering is when we convert that intermediate representation to LLVM IR. So LLVM is a general compiler library. It backs Clang, all of these things, and is the reason that Numba can be as lightweight as it is that we can defer the entire back end of our compiler to this library that all of these hardware manufacturers contribute to and ensure works optimally on their hardware. There's a related library that NVIDIA has called NVVM, which is a fork of LLVM that understands a slight variant of the LLVM IR syntax for compiling for NVIDIA GPUs. So we actually switch between those depending on whether we're doing CPU or GPU work. LLVM produces all the machine code for us, specialized for the CPU you're sitting in front of. So if you're sitting on a Skylake, you get to use AVX 512. If you're sitting on Broadwell, you might only get AVX 2. It also caches that code in memory so that the next time you go through this entire pipeline, you just skip directly to the dispatcher and execute, so that all of this compilation overhead is only incurred on the first call. After that point, it's just the cached object code is just executed. So slide 9. So Numba, one of our goals, because of honestly our customers who use all kinds of platforms, they're not Linux specific. Numba is designed to work with Windows, Mac, Linux, 32 and 64-bit CPUs, NVIDIA GPUs, and we have experimental support for things like ARM, Power 8 and 9, AMD GPUs. That'll be improving shortly. Also, because some of our users are using Python 2, we support Python 2.7 in addition to 3.4 through 3.6, and basically all the current versions of NumPy that someone might want to use. All right, slide 10. So Numba does a bunch of things. It can, as I mentioned, it can detect CPU model during compilation. It can generate multiple implementations. So if you call a function with int32 and then int64 and then float32 and float64, it will actually generate 4 implementations and dispatch to the correct one in memory. So that from you, the user's perspective, it looks like you're getting the wonderful Python duck typing where things just work regardless of what types you pass in. But we're actually generating new implementations that are specialized for the use cases you've given us. You can call it to C libraries using CFFI, which we've had people use to interop with external libraries. There's actually a special callback decorator where sometimes what people will do is JIT like an inner function that you might pass to an optimizer, like your objective function, and you want to create a function with a known C signature and then be able to call out to it from some external optimization routine. We have some support for caching to disk, ahead of time creation of shared libraries, although I would say that these are, there are certain kinds of code we can't cache to disk for internal reasons. And our goal is the compiler is extensible, and you'll actually hear about this in Jim's part of the talk, where you can extend Numba quite heavily for new data types and functions and all sorts of things. So slide 11, I just wanted to call out real quickly that LLVM does auto-vectorization. So some for loops, it can identify as being executable using vector instructions, which can operate on multiple elements in parallel. And the nice thing about a JIT is that you will generate code for the particular vector instruction set you have access to on the machine you're sitting in front of. whereas oftentimes if you compile ahead of time, you have to decide at what level you want to support. You might say, okay, I'll support AVX, so only Sandy Bridge and later, let's say. But then you're missing out on AVX 512 if some of the machines you have newer processors. So, slide 12. So one of the things to note is that because in no Python mode, we can get rid of all the Python objects, we can also release the GIL. The global interpreter lock in Python is often cited by people as being a huge obstacle to scaling with multiple threads because the interpreter itself can only run on one thread at a time. Inside of compiled code, you can release the GIL. So like things like Numba and, things like NumPy and Pandas actually release the GIL in key functions that they've implemented in C for speed. Numba can do the same thing for code that you compile with it. So you can pass a no GIL equals true, and when Numba enters this function, it will release the GIL, which actually enables you to use things like concurrent futures or other threading systems, Dask even, in Python to get, speed ups just by running these functions in parallel on different threads. Slide 13, I'm not going to have a whole lot of time to talk about this, but ufuncs, universal functions, this is the concept from NumPy, which is very powerful, which is that you can describe math operations that are implicitly spanning differently dimensioned inputs. So that you can say a array plus a scalar means that I want to broadcast that scalar across every element of the array, but you can also add two 1D arrays. You can add a 1D array to a 2D array, and there are rules for how to do all of that. And the great part is that those functions that can accept multi-dimensioned arrays, you can make those in Numba. So if we go to slide 14, it's a different decorator called vectorize, where inside of it you write a scalar kernel. You basically just say, look, this is V and gamma are scalars. What am I going to do and what am I going to return? And Numba will automatically convert that into a ufunc, which can operate on any dimension array following the broadcast rules of NumPy. It's a very powerful abstraction. The other nice thing about ufuncs is that they're implicitly parallel. They're embarrassingly parallel, in fact. And so our vectorized decorator will allow you to specify a target that isn't just a single-threaded CPU. You can actually target our thread pool, and so if you say target equals parallel, we'll generate a multi-threaded implementation of this ufunc for you that just will automatically use all your cores that are available. If you go to slide 16, in addition to that, we have, due to some generous contributions from Intel, a optimizer path called the parallel accelerator, which can actually do some code analysis, loop fusion, and other things in a function to make even more efficient parallel code automatically for you. So things like array expressions and random functions and dot products and all these things that you might just write NumPy code in a function, parallel accelerator can analyze those and fuse them into a fairly efficient multi-threaded implementation. I'll keep cruising here because I want to make sure I give Chris some time. If you go to slide 17, there's an example here of the update process in logistic regression. Parallel accelerator does a whole bunch of loop fusion and things in here to result in code that's even twice as fast as what Numba would have generated. If you go to slide 18, p-range is effectively OpenMP for Python, so you can specify a for loop can execute each iteration in parallel. Actually, let's skip down to slide 21. You guys can look at the other slides later. I want to talk a little bit about GPU computing. So this is, Numba also entirely has built into it a GPU compiler, which has sort of two approaches. One of them is that ufunc compiler I mentioned. You can target the GPU, so it will actually handle all of the data motion and converting it into a parallel GPU function and all of that. Another approach is that you can actually call CUDA kernels in Python syntax. So if you've ever used something like PyCUDA, which from Python lets you call CUDA kernels written in C syntax, Numba has an equivalent, but it's all in Python sitting inside of the same source file. And we're actually working towards better interop with all of these different tools. So if you go to slide 22, here's an example of a CUDA kernel that does histogramming. This is one of the first things I ever did. I've been doing GPU computing since about 2007. One of the first things I ever did was something like this. It's hugely sped up by the GPU, and you can implement it right here in Python. So slide 23, just to get a little bit about sort of the future, we're aiming for Numba 1.0 in 2018, this year. Our goals are to improve some of the diagnostics. A lot of the feedback we've had is people want to understand when things are slow, why they're slow. We actually are planning to rewrite our UFUNC compiler to resolve some limitations. We want to have a way to actually, inside of a NoPython mode function, jump back out to the interpreter as sort of an escape hatch for things that Numba can't compile yet. We want to make sure we're solid on all the major architectures, so we're pretty, we're excellent on x86 and NVIDIA, and we need to get better on ARM, PowerPC 64, and AMD. And we want to clearly document all of our compiler extension points so that when people write extensions like OAMAP, they're sure that they're using things that will be supported for the entire Numba 1.x lifetime. After 1.0, we want to rewrite our type inference. There's a couple of different sort of Python constructs and idioms we can't support because our type inference can't figure out what's going on. So we want to improve that. We want to broaden our data types. We're very interested in the Arrow story, how we interop with Arrow. C++ interop is the current limitation of us. It's just very hard to figure out how to call C++ from generated code if you don't already generate C++. So Cling may be actually an avenue here. And other integration. I mean, actually, Numba plus PyPy is not as crazy as it sounds. So skip 24, you can look later. These are just some tips on when Numba is a good idea. And then finally, jumping to the conclusion slide, I just wanted to show you, these are a bunch of links if you want to learn more about Numba, either looking at our docs, if you want to see a tutorial for both CPU and GPU code. We have both of those. Recently, the lead developer on Numba gave a great talk at AnacondaCon about ways that people have used Numba, all sorts of projects, including OAMAP actually, which is an interesting watch just to see how people have used Numba in the wild. So with that, I'll go ahead and stop so we can jump over to Chris.
Great. Thank you. And are there any questions before we switch to Chris?
Yeah, I have a question. How you deal with the case when you'd like to deliver the code on premises where the dependency change should be in place? Because you said on the slide somewhere in the beginning that the first time you hit a function, it will be compiled. It implies that I need to have the entire infrastructure in place, even if sometimes I don't know what the code is doing. I mean, I can grab it from someone else and would like to run it. So how it would be packeted stuff?
Yeah, so if you're taking advantage of the JIT functionality, you just need to have Numba installed in the Python environment that you're going to run, and that will work. There are ahead-of-time compilation support allows you to, in some cases, generate libraries that don't depend on Numba anymore. They still depend on NumPy. So you would still need Python and NumPy on the target machine, but no Numba. Those, I would say, is not as useful. The other thing we've actually had some people do is actually pre-populate the cache so that common specializations are already present and deploy that. There you still have to have Numba present. But Numba is designed to be pretty small. It's about, depending on your architecture, somewhere between 60 and 100 megabytes. It does not, for example, require LLVM to be present on the machine. We actually statically link only to the pieces of LLVM we need to try and keep it as small as possible. But it does require it to be available in most cases on wherever you're deploying to. But you would have the same problem with your other Python libraries.
Yeah, but it means that it's doable just to basically do the pre-compilation up front and then already deliver the caches. That's my understanding, right?
Yes. You can either do the caching case so that if you hit a case you haven't compiled, you will, or you can do the ahead-of-time compilation, in which case if you hit a case you haven't compiled, you get an exception. Yeah, those are possible.
Actually, could I ask this question that came through the comments so it doesn't get lost? Is there any thought to add tracing extensions to Numba, as tracing JITs often do better when there's a lot of cross-function calls?
Yeah, that's something we've talked about for a post 1.0. Right now, for our goal for 1.0 is to stay pretty narrowly focused on what we're doing now. But yeah, that has come up as something we would be interested in investigating. I think this is part of the reason we need to upgrade our type inference system, is to allow code that hasn't been specialized yet to exist in a function, and then have the ability to upgrade it as you would need in a tracing JIT. This is actually one of the reasons why I'm curious to see if there's a possible interop between Numba and PyPy. PyPy is an excellent tracing JIT, but lacks some of the ability to do GPUs and other things that Numba has, and so there actually is a potential there for them to be used together.
Okay.
But we just haven't done the plumbing to make that work.
Okay. Okay, thanks. Any other questions?
Yeah, I had one. I was just curious how tricky it was on the Numba side to make the GPU code, because I would imagine that it's good for sort of short functions, at least. I mean, because there's all of these kernel optimizations that have to happen to have any sort of efficient CUDA code. So, I mean, how are people successful in switching to the GPUs?
It actually has worked pretty. If you take a look at that YouTube link, there's a project. Was it Livermore? Some physicists there actually implemented something. It's called FBPIC. I think it's forget the exact name, what that stands for, but they implemented a GPU accelerated Monte Carlo basically because they needed something simpler than the giant C++ thing that they were working with in order to be able to iterate. The main thing to note is that and this is actually the great thing, is that because NVIDIA's compiler has this LLVM-like front end to it, a lot of our code generation is actually shared between the CPU and GPU compilers. And the back end of it is entirely the same compiler that you get with the usual NVCC CUDA compiler. So all of those optimization tricks and stuff you need to get efficient GPU code it's the same ones NVIDIA uses on their C compiler. We didn't have to rewrite those. So it actually was easier than you might imagine to get all of that stuff to work.
And can it choose automatically between the CPU and GPU?
No, we still make you do that decision because we don't have really good heuristics to decide when that should happen. One thing I kind of briefed through is we're actually working, there's another project out there called CuPy, which is actually a almost complete re-implementation of NumPy and all of its functions for CUDA. But it gives you like a almost literal drop-in replacement for NumPy. And so we're working with those developers actually so that you can use Numba compiled GPU kernels with CuPy instead of with our own arrays. So you get initially out of the box sort of the ease of use of using CuPy arrays, and then can combine it with custom functions you wrote in Numba. But we still make you make that choice just because we don't have a good heuristic to decide to do it for you yet.
Okay. Okay, thank you. So now as we move to Chris's talk, Chris, don't worry about the time. My talk is expendable. We'd really like to see this use case.
Well, I want to see it. I want to see your talk as well. So, but what I'll do is just essentially explain a use case, and then we can get into discussions to see who wants to hear more about what side's it. Hold on. Let me make this bigger. Size. Is this readable? Should I go full screen? You can see it?
No, it's readable as it is. Yep.
So Stan was talking about making tools for people that make tools for then analysts. And that's essentially what myself, Chris Tunnell, and Jelle Alberts, who's a student at NICAP, have been doing for the XENONnT experiment. So what is XENONnT? Since I think most people here are collider physicists, just the quick lowdown is that it's a xenon liquid dark matter detector that's in the Gran Sasso National Laboratory in Italy. It's instrumented with about 248 PMTs with 10 nanosecond flash ADCs. So we need this very quick timing. It's a TPC. So between these flash ADCs and all of these PMTs, we can actually produce quite a bit of data. And the use cases that I'll be talking about Numba within XENONnT is an actual real-world implication, since this is a world-leading dark matter experiment at the time. And I can tell you about the microphysics if you want, but moving on. So there's a bit of a challenge. So before explaining why Numba, I need to explain to you the challenges in software design that I see. And I see sort of three key challenges where these are, one, changing requirements. So through different experimental phases, you have different requirements in the software. That means you always have to be adapting. And if you don't do this well, then you create a mess. And this happens as you understand your detector better, which happens through the years, or as the sort of physics priorities of the experiment change, so you need to start doing better things. Which means that this requires essentially constant refactoring type what I call enhanced approach. The second thing is that often we have small teams doing sort of the software, the core infrastructure of an experiment. And even though every experiment of every size complains about the lack of skilled people, I think that this sort of concept of having small teams responsible for the key software challenges is quite universal. So this means that we have to make sure that we handle the technical debt and invest time to keep the code base coherent and manageable, because otherwise it goes out of hand. And then the last thing is just this constant battle against legacy, where we all know physics software where we can't essentially change it without knowing if it's broken or not. We suffer from this, just publication pushes, high personnel turnovers, and the rest, where this requires a certain amount of testing to allow for, once again, sensible refactoring. And at the end of the day, you really want to struggle to keep things as simple as possible, because this is the only way to ensure the sustainability of the project through the years. So the design decisions we made in XENONnT 1-ton, so this is the picture that I was showing before. XENONnT N-ton is our upgrade we're building at the moment. So we decided to have, to use the scientific Python stack as essentially the main thing supporting our codes, ranging from the data acquisition to the event reconstruction to analysis later on. The reasons for this was that it was a mature code base with a large user base that was actively developed, and then don't underestimate how much transferable skills was important to all of this. A lot of postdocs at the time thought that they would be working in industry like Stan. So learning these skills was nice for us. But at the end of the day, going down this Python stack route meant that we were a bit more resistant to technology lock-in. So I've seen various neutrino experiments. I've bounced around many experiments where they sort of get stuck into some technology paradigm that they can't get out. Going down this route helped us essentially mitigate that. So the code I'll be telling you about in a minute is a pipeline programming sort of paradigm, where this is actually based on, extending the philosophies that people on SNO, and then also Stan's, it's called RAT, it's still used within neutrino and dark matter experiments. There were some code bases developed about 10, 15 years ago. This is all extended. So one of the key things with Python was that it made testing a lot easier and sophisticated, which helps then, keep the whole code base in line. But then the one thing you're wondering is, what about speed? Python's slow, right? And then with Numba, the normal things that we think about Python might not be true. So at least Python development for low-level code. So the speed requirements that we have is that we have to be processing about 500 megabytes a second of data within the DAQ, within the acquisition level, and then a petabyte a year in offline processing. So that sort of sets the scale of the problem. So it's not nothing. And one, it's a tricky thing there are a lot of caveats with this, but physics software in C++ is almost always slower than Python if you go in this direction. And the reason for this is that profiling and refactoring of large programs in C++ is very involved, requires large costs. So the caveat is if you can just compile your key bits of Python code, this can be true. And then this is an in-practice statement due to the overhead of writing optimized C++ code by physicists. So you can fall down this essentially trap where you go down this road, you get stuck in it, and you're unable to refactor, so then you start slowing down the time. So then you say, well, why not just have C++ routines with Python as a glue language? So I've tried this on various experimental frameworks before, Swig, Boost, you name it. But the key trouble there is these multi-language packages or frameworks essentially become a nightmare for the maintainers, a sustainability challenge. Beyond having to maintain these with different style guides, doubling your dependencies, to how do you test a program that splits over two languages with the appropriate coverage to readability, it becomes much harder to understand what it's doing. It's even silly things like throwing exceptions over languages or being able to track down why your Python is segfault becomes tricky. And even the way in which our code interfaces with root. Root is a large dependency where you can already start seeing some of these issues where root will change the import behavior, or the development cycle of root is different than a lot of the Python tools, which means then you sometimes get stuck into Python versions to keep the root side working. And this just is all, if you start relying on two different software stacks, then you sort of span two ecosystems that might not be so compatible. So then why not just write Python code that turns itself, at least from my point of view, into C code when slow, i.e. Numba. So what we did within the XENONnT project was we developed this infrastructure for about a year of just quick prototype in Python, run snakeviz. This is this thing to the right where you can see how slow code is, and it's hierarchical as well. So prototype in Python, profile, then Numbify or refactor the slow parts, and then rinse and repeat. Just keep repeating this cycle until you see how much speed you can actually get out of things. So use case one. This is the XENONnT one-ton DAQ, which just some comments on the setup. So we have asynchronous digitizer readout where the payload is time channel data. And what this means is every time one of these PNTs sees a photon, we actually record out the whole waveform with the 10 nanosecond sampling. And we use, within the data acquisition at MongoDB, for internal DAQ communication, where this is handling about 1 million inserts a second. And then the idea is once it's in this database, which is handling a lot of our time sorting operations, then we can have some Python code or the software trigger that then does our event building. So then if a student was to say to you, I'm going to make a data acquisition in Python, you would say, you're mad, you would get rid of them. But I hope, well, to convince you that it's not as silly as it sounds. So within a software trigger and event builder, you have many different tasks on the data acquisition side, like clustering signals, splitting signals, sorting PNT signals, and deciding if they're triggers. For these are all array operations. So I guess just briefly on, this is just a schematic. We have a digitizer where these are read out over optical links from various reader PCs. Remember, there are 248 PNTs. And then all of these readers, these are just computers that are CON flash ADC to MongoDB interfaces. So that goes into MongoDB, where then we distribute it over 3 computers that I guess there's about 120 cores between them that then do all of the processing on top of this database, building the events, and this all goes out to raw data. Just to show you a bit more pictorially what our data is looking like, to understand why arrays are appropriate. So we have pulses. These are just PNT pulses. A photomultiplier sees a photon and makes this pulse in in the PMT. So we just have lots of these waveforms where all of these have times associated with them, where then we can cluster them into signals, where then from there we can say, well, should these signals have triggered, and then we can define some event ranges based on this. So these are lots of time series that sometimes require sorting, clustering, rest. So an example of one type of Numba routine, just to start simple, is we numba.jit, just some routine that's get PMT numbers. So within the data acquisition, we have modules and channels within that module, and we want to know which photomultiplier to location that corresponds to. This is just a quick loop. It would be slow in Python since you have Python objects, but this is something that Numba is quite good at compiling. You can see the link to the code there. Same sorts of things. So on example 2 for the DAC, we have classify signals. So we have different types of signals, photon and electron type signals, detector that we want to know which type of signal these are, so we decide to trigger on it. This is just looping over signals we're seeing in the detectors based on their time properties, assign signal types to it. Once again, it's just a type loop. And these are the types of loops that we have. So once again, you profile, you find the slow code, and then, well, speed it up. And these can even get this is just example 3, finding essentially gaps in data. This is a type of clustering routine. But you see, I don't want to get into the details of the code beyond that. These are just some simple for loops, and it would be quite obvious to you how to write this in C code. And at the end of the day, so this is DAQ speed at the moment, so the trigger processing rate versus DAC rate. And let's see, so the red dotted line that's going up and down is about well, it's our design rate. This is 300 megabytes a second. So we're able to process through the software trigger at about that speed through Python. Where the caveats is I couldn't make lines corresponding to our original rates any lower, but when we were just trying to write C++ code to do this, we were getting, well, quite slower behavior, or Python only was, I think, 0.1 to 1 megabyte a second instead of a few hundred. And that's also per core, so we probably got up to 50 to 80 with Python only. These were all numbers that changed a lot. Okay, so on to use case 2, event reconstruction. So it's a TPC. This is the first signal. This is the later signal, right? The time between the signals gives you depth. You have to reconstruct these signals correctly to be able to do anything. This is a high energy signal, so it looks quite nice. When you go to low energy, you begin to see a lot more craziness. So every one of these red dots is a photon that was detected. Here, you see as a function of time, these are amplitudes of signals in the detector, and you just see that there's like 100. Within any drift length detector, you have like 100 signals you need to figure out. So these are essentially lots of loops. And once again, you can profile your code. This is the profiling of packs, who we have on GitHub. And this is after quite a bit of optimization, but there are many different bits and pieces that go into the pipeline. So you find out what's slow. In this case, it's a clustering algorithm that address that and see if you can write any Numba loops to help or refactor in some way. So the event reconstruction runs on about an hour of data and finds all hits within any given event in the detector. And the challenges are, yes, you have all of these steps along the way that you then need to profile. And there's no one optimization that gives you a factor of 2 throughout the whole program, but it's really you have to hack away at it function by function, at least doing it this Numba way. And the things that we use Numba for within XENONnT are building PMT hits, integrating waveforms, clustering signals, computing properties of signals, baselines, and the like, and grouping. So once again, this is the same sort of, oh, maybe I actually, it looks identical. Maybe I actually copied the same code again. But the sorts of functions we have with it later down the data pipeline. I mean, it's the same sort of thing, figuring out what types of signals. In XENONnT, which is the detector we want to have online in, I don't know, a year or two, depends how optimistic you are, we're wondering how much we can redo the software stack that we have, but with a bit more of an array focus. This is using our knowledge from having built XENONnT, where, okay, we started building it a few years ago. The big results have been over the last year or two. The lifetime of dark matter detectors is quite short, so you already have to begin on the next one. So we're wondering if we should abandon the event class internally and move towards arrays or OA math or anything like this, because then it's Numba-able, NumPy-able, serialization is quite a bit easier. You don't have object creation costs. The event class that you're passing around throughout these programs, I think, is an artifact of how software frameworks were originally developed based on the root event class and how that was serialized. So if we switch more to if we break that paradigm, we can get a lot of these array optimizations. But we also want transparency of being able to switch from database files and the rest. And at least at the moment, the speed tests, redoing it in this way, are quite promising. About 100 megabytes of core. This is something from, Jim, I think I just want to, so giving it a rethink, this is just a picture of the cheetah, rethinking how we're doing it and trying to rely a bit more on these Numba optimizations and array optimizations really seem to be giving us some great speed increases, getting us up to about 100 megabytes per core even, in being able to process data. So at this point, I think the conclusions are just incredibly short. Numba worked in our use case. It could help with others. And at this point, are there questions or we can discuss any details?
Are there any questions out there? Hello, are we still online?
Maybe I will.
Last chance. Any questions? Real use case. Actually using Python in a DAC and an event reconstruction.
It was too dark battery.
Actually, personally surprised to see that worked as well as it did. So I'm excited to see these slides. But
yeah, I could show you on some of the things that we're doing. For upgrades as well. So the whole idea was just to have some. What we're considering is just having some allocated array, essentially, that then you just keep feeding into, so you avoid object creation costs and the rest. And then, being able to, if you can somehow express all of your operations as somehow some vectorizable thing, then yeah.
I'm curious, do you suspect any of the pipeline would benefit from GPU acceleration, or are you just not processing enough data in bulk? I imagine if you're trying to minimize latency, you might not have big batches.
You sort of have, maybe. We haven't tested it yet. Most of the GPU work we've done has been for TensorFlow or things like this. But this would have to be specialized equipment that then we brought into the data acquisition, which is, of course, not a problem to do, but we just haven't really investigated it. It could, I just don't know. There's also, since we parallelize within the data acquisition, sort of above the level at which we're doing all of these Numba calls, then you start having two different systems doing parallelization. So, which I guess isn't an issue. I don't know. We just haven't thought about it as much.
Okay.
A generic
Well, thank
question.
you. Oh, yes,
Sorry,
David.
About
Go for it.
optimization, you talked quite a bit about it. What was your impression of the Python optimization tools? Did you you showed sort of function level monitoring? Did you have success going beyond that, or did it just become handwork at that point?
You mean going lower level than just functions?
Yeah.
So we never went down that low. So we would use SnakeViz, which is this fancy, I don't know, sort of shows the whole tree and how every call or sequence of calls contributes to it. And then at that point, we would be identifying essentially a block of code that then we could rethink about. But I mean, I always get the feeling that if I'm looking at bytecode or I don't know, assembly code in other languages, then I wonder if I'm doing something wrong. So
on that note, actually, I was going to say, if you're not for Numba functions, but if you're optimizing, I found this super useful in functions that end up with a lot of stacked up NumPy operations. There's a project called Line Profiler that is more useful in Python than it would normally be in something like a compiled language like C or C++, where lines move around because of the optimizer and all that stuff. But when you're just making NumPy calls, I found Line Profiler to be insanely useful, if that ever comes up.
So we had tried that. I think since there are many different, essentially, stages in the processing of the data acquisition, that SnakeViz lets you also see bigger picture, where things are slowing down. But you can also get down to the sort of function level call. So it gives you both scales.
Okay. Okay, well, thanks. So I said that my talk was expendable, and by that I meant that I'll give my talk. So if people are free and available to see it, they can stay, and I think we can keep recording, so it'll go onto the YouTube video. But since we're like 2 minutes in the end, I think I'll go 18 minutes over the end. So those of you who are interested and have the time, I'll launch into my talk. And those who have other commitments, I understand. So first, thanks, Stanley and Chris. I may not get another chance after when you need to go. Okay.
Yeah, I have to jump off now, but thanks for having me. And again, if people have any questions, Jim can give you my contact info, and I'm happy to answer any number of questions you might have.
Okay, great. Okay, so are my slides up? Oh, I can see that they are. Good.
Yeah,
so,
no problem, Jim.
Okay, so whereas Chris's use case was a real using Numba directly for experiment code in production, I'm developing a library that has not gone into any kind of production and also hasn't seen users yet. But this is a way things can go. So page 2. We've seen that Numba provides a smooth transition between high-level tinkering in Python and high-throughput processing, and we've also seen a real-world demonstration of it. But now the question is, can we use Numba for the LHC? The first question for that is that it must, can it access root data? And for that, there is a solution, or there are several solutions. The one is I developed Uproot, the Python package that views root data as NumPy arrays exactly for this purpose, because I was knowing that I was moving in this direction. It's found some other use cases along the way, but this was its reason for being, as well as 2 pull requests in root that add root object to NumPy array in a future version of root. Also for the LHC, we will need arbitrary length lists of particles per event, not rectangular arrays. we will not be able to express our even the most refined AOD level information that goes from the centrally produced to the end user physicists. It can't fit into NumPy arrays. Or I should say it can't fit into rectangular arrays. And then the alternative to that, using some of Numba's fancy features and being able to represent structures through, say, lists of named tuples, this would be a serious performance hit, because even though these can run quickly in Numba, you have to feed Numba with a Python object, so you would have to turn all the data into Python first, and that's not feasible. So the solution that I've been working on is something I'm calling object array mapping, or OAMAP. The reason for this name is that it's an analogy with object relational mapping, ORM. ORM translates between classes in an object-oriented programming language with relational tables and databases. This is a bit different from that. It's translating between the same classes and object-oriented programming, but this time with low-level read-only arrays. So unlike ORM, we don't make any promises about being able to have transactions adding to this the way that you would in SQL. You know, they really are bare metal arrays. So it wouldn't have the kind of performance problems that an ORM like objectivity did. So the goal of this project is for physicists to be able to write arbitrary code, assuming OOP-style objects. The actual data is stored in arrays, such as tbasket, you know, an array in a root file, but then never deserialized into objects the way that root does. And then the physicist function is translated into operations on those arrays, rather than translating the arrays into objects. So we change the code instead of changing the data. So the data is big and the code is small. So this, what I'm describing here, is a kind of compilation. Last year I was giving talks about femtocode. I was developing a language that would do this compilation. But then I realized we don't need a whole new language. This is really just data representation and handling. So I was able to simplify things and just do the data representation and handling without the rest of the language. Maybe the rest of the language will be developed someday. It's, you know, pet project. I would love to do that, but let's, you know, focus on the thing that's actually needed. So what I'm talking about here could be done in C++, presumably. It would probably involve a lot of template arithmetic. But my observation is that Python is a high-level language that physicists already use, and Numba provides optimized compilation through LLVM. So at least the first version of this can be done in Python and can be useful in Python. Early in the stages of this project, I did a lot of performance tests before actually designing the library. I wanted to make sure that when I decided to, you know, when I gradually decided to commit to a library for the compilation part, when I found Numba, I wanted to make sure that committing to this library and requiring it, needing it, wouldn't give away performance from the start. And I observed that this is not true. There's no loss in throughput compared to pure C. If I were generating C code from and then compiling that C code, it wouldn't be any faster. The plot on the left is showing just how far you can go. These are 4 different analysis-inspired functions that you might perform an analysis. They're single-threaded rates that, if you're up, they reach millions of events per second. And kind of the fun part of this bar chart here is that of the 4 functions I tested, the one computing masses of pairs of muons, was the slowest, not because it's a doubly nested for loop which rejects duplicates. The same is true of the fourth one on the right. It's slowest because it involves trig functions. Removing the trig functions is what releases the bottleneck there. And the difference between green and purple is where the data is coming from. Are they coming from root with bulk I/O, which is a future PR, which is very fast, or are they coming from cached arrays? From cached arrays, it's much faster, showing that evaluating this code is not the bottleneck. Then an even more impressive thing that I saw, the other plot, is that for multi-threaded scaling, if you try to do this with many threads, it's limited only by the physical memory bus bandwidth. So I found some hardware, Knight's Landing processors with the MCDRAM that do not have, they don't go through a memory bus, and was able to release a limit on multi-threaded scaling. So really, even committing to Numba, there's no ceiling on how fast it can go, other than the hardware ones. So moral of this is, if we can deliver arrays to main memory and then to the CPU cache quickly enough, and this is the hard part, and physicists' analyses can be expressed as array operations on this sequential data, then it can be compiled to run at this scale. So instead of converting T-baskets into objects, let's convert object-oriented code into array code. To do this, we can't consider the entire type system of C++ or Python. We need to consider some general enough data types because we'll need to emit special code for each one of these data types. So here's the type system that I'm implementing. Primitives are any fixed width data, such as numbers, Booleans, that sort of thing. Lists are arbitrary length collections of data with a given type. So these are homogeneous lists, like STL vectors in C++. Unions are a set of possible types that allow us to have some heterogeneity, some polymorphism, like you would expect from class inheritance in C++. So you can make a list of electrons or muons. Records are objects containing a set of typed fields, so you might call them classes or structs. Tuples are fixed-length collections of typed fields. Actually, tuples have more to do with records than they do with lists. So they're kind of like records that have index positions instead of field names. So their implementation is almost the same as records. And then pointers are perhaps the most interesting for this. So these are not absolute addresses in memory like a pointer in C. These are objects identified by position in another field, so it's a relative address. It's intended for linking relationships among particles, such as this jet has a muon and here it is. But it's outgrown that initial use case. It's also useful for expressing skimmed data as event lists, for making non-tree data structures, for emulating Arrow and Parquet's dictionary encoding of categorical strings well beyond HEP. Pointers are actually a surprisingly enabling part of this. The data types and their representations, all of these things, they have what I'm going to call compositional symmetry. Any type can be plugged into any other type, so we're not limited to lists of just one kind of thing. It could be lists of lists of lists of lists of records of lists of unions of pointers of primitives. And then the representations follow suit. And with that symmetry, we can write recursive code that handles all of the infinite possibilities you would get by combining these. So to illustrate what's happening when we're representing a nested object as arrays using an example, here's an example of a list of record of two attributes. if you had data like this and you had the logical data that's written out with square brackets and parentheses, so that logical data is what a user might see. It can be split into 4 separate arrays of different lengths that can fully represent that structure. This splitting, in fact, I'm using the word splitting like root uses the word splitting, is what root does in order to separate things into T branches in a file. Only difference here is that we are continuing to use it that way at runtime. So I've written this example. You can follow it that each of the primitive attributes are just written out, ignoring their event boundaries, and then where the event boundaries should happen is encoded in arrays associated with each list, the inner list and the outer list. And I've written down some rules for how this example works. Of course, we have other data types, so there are more rules than are shown here, but this is giving sort of a taste of how you would split the data out into arrays. And then proxy objects, something that you would have at runtime, they only need to know where they are in the schema. That's something you only need to know at compile time. And they need to know where they are in their arrays. That's just an integer index at runtime. So you've replaced all the structure associated with, say, a C++ class instance with just an integer index. I've mentioned several times that this is similar to root. In fact, the transformation rules, I tried to make them as similar as possible to root, and also Apache Arrow, which is an in-memory split data. And as much as possible, that's the caveat. Some on-the-fly transformations would need to be applied to read root into OAMAP or read arrow into OAMAP, but these have been designed to be minimal. But unlike root, what OAMAP is doing is it's performing calculations on the columns in memory, whereas root stores the data in columns and then constructs objects. And unlike arrow, OAMAP performs arbitrary functions, even procedural code, on object-like data, whereas the main thrust of arrow is to deliver a data frame model, like a pandas data frame, and perform data frame operations on it. So, and also unlike both, which are focused on storing data either on disk or in memory, OAMAP, the focus is on calculation. So really any software that provides arrays in the right format or on the fly converts them to the right format can be used as sources. So here's an example. Here's a root file. And the caveat, old root interface, I broke this a few days ago because we don't have users yet and I can redesign at this level. But we can read root data into it by pointing at a root file. Here I'm using uproot because that just lists them into NumPy arrays. And then the OAMAP schema both describes the structure of a deeply nested object, and it also points to the names of the arrays that are used to serve the various parts of it. In this case, those arrays are all T-tree branches. And so when you are working with one of these objects, let's call it events, and then you ask events0.muons and then events0.muons.px, it fetches the column of data from the root file on demand. And so even though these objects, they look like Python arrays, and the arrays come from root, or they come from Apache Arrow, or HDF5, or whatever. So, okay, so now that's enough background about OAMAP to explain, why it exists and why we're considering embedding it in Numba. And now I'll talk about how we embed it in Numba. So I was talking about these objects you can play with on the Python interpreter. Well, that's great until you want to do something fast. So the original plan for optimizing this, for transforming the code from object-oriented code into array code, originally I was doing transformations of the Python abstract syntax tree, which is something that Stanley mentioned in his talk that Numba doesn't do anymore. It goes to, all the way down to the Python bytecode. So I was doing these AST to AST transformations, which is essentially taking a programmatic view of the source code and turning it into another view of changed source code, replacing object references with array references, and then with the changed source code, you could either run it directly for debugging or call Numba on the result. So this required me to do my own type inference, which you can do by stepping through the OA map object. But if some information relevant for the type inference comes from some object which is not an OA map object, like it's some Python object, then I would need to re-implement all of that. So I saw value in embedding this object to arrays transformation in the Numba compilation pass itself to gain the integration with those other Python types for free. And then the thing I want to say about Numba here is that they have this extension mechanism so that anyone can do this. Currently, it's not for the uninitiated, and when I started it, I was uninitiated, and I had to learn the hard way how to do all of this stuff, but it is possible. There are hooks for doing it. And there's even some documentation, which I'm showing on the slide. I'm going to first show the end result of all that. The end result of that, what we want to get out of this, is for a user to be able to write a function, such as this compute function that computes dimuon masses, and have one of the inputs to this function, this events, be an OA map object. It's the same one as on the previous pages, a few pages ago. And be able to walk through this object and compile it into and emit the right LLVM bytecode to enter it into the compiled function in such a way that gets rid of any object references at runtime. So I'm doing the objects to arrays transformation. So here we're looking at this compute function. The events come in, and it just does the right thing. And you didn't even need to know anything about OA map. You just know that Numba asks you to say @numba.jit before the function, and it will compile it for you. And that's what you get out. So you can run this. On page 13, I'm showing a taste of what had to be done to make this possible. So there, in the block diagram that Stan showed, there was a typing phase when you infer all the types, and then you do another pass to transform the Python bytecode into LLVM bytecode. That's what the first and second functions do here. These are implementing list brackets, removing a lot of special cases, and checks for safety and such, so I can fit it on one slide. You see the typing, they're just Python if statements. You can put any kind of code that you want to determine how two types combine to make a new type. You can do whatever you want. And then the second function, you can do whatever you want, anything you can express in Python to emit the right LLVM bytecode to run your function. So in this case, the first stanza of that second function is just loading some data, getting it into some useful form. The second stanza is implementing the Python negative indices. And you have to do this by allocating space on the stack doing an if-then with a LLVM instruction, adding some stuff and then pulling the result off of the stack, it's very low level. And then the last stanza is doing pointer arithmetic to find that place in the array. And then generate is a recursive function that does this again for whatever might be inside of it. So if you have a list of lists, it'll do this twice. So just want to show here, there are hooks for doing anything that we need to, including if we find a performance bottleneck, we can do something, we can emit different bytecode. So my conclusion from this talk is the benefits of implementing OAMAP in Numba. So Numba is a mature type-inferring Python compiler feeding to LLVM, so there's a lot that I didn't have to do. Numba's extension mechanism lets me write arbitrary logic to infer OAMAP types and emit the right specialized bytecode. The OAMAP proxies can be passed into or out of any JIT-compiled function like any other Python type. So now there's no special thing that anybody needs to call. This compilation pass, not only does Numba go through the function that you ask for, but if you hit any functions that it calls, it goes into those as well. So I get, as a side effect of the compilation process, a list of all of the arrays that this function and all the functions it calls, all those arrays that it touches. So before we enter into the calculation, I know a complete list of arrays that need to be selectively read from root, and we never read too much. And then finally, there's low-level access to fits performance bugs if they arise. So that's my conclusions. The next slide is about the future of OAMAP, but at this point, I'll take questions.
Where do you see OAMAP fitting into essentially the HEP software stack? So would this be analysts writing it, or you expect it to be one level lower?
Yeah, my primary intention is to make it one level lower. If you've seen any of my talks about a query server, that's what this is being developed for. This is the execution engine for a query server, so that someone can type a Python function that fills a histogram, send it to something in the sky that splits it over all the data, compiles and runs, and then returns the histogram that the person asked for. So that is my intended use. However, I'm also developing it in such a way that advanced users can use it directly before such a query server exists, because I do want to get feedback, just like OAMAP. Sorry, just like Uproot. It was designed to be a backend that would feed into OAMAP. That was the purpose. But I made it general enough that advanced users can use it for other purposes, and then get back to me with bugs and feature requests and all of that.
Well,
and that's been
even not
successful.
advanced users. The Xenon 110 analysts, for instance, use it. So, Uproot. Okay. And maybe this is getting off topic. Warn me if it is, but what are sort of the timescales of, say you're working on OAMAP and then you were talking about this query server, but is this like you falling down the rabbit hole and just having to make things as you get back up? Or is there, progress on other fronts that this plugs into?
Mm-hmm. Yeah, so I have something of a deadline to develop a personal deadline to develop a working prototype query server at the end of 2019, which is the end of the Diana project. So I want to have that to show for it at the end of 2019. The first component was getting the data from the root files. The second component was execution engine, in other words, OA map. The third component, move on to my last slide, is being able to distribute this. And there I'm looking at Dask, but I have to make these objects so that you can have a remote handle on them, right? So you can, like a Spark RDD, you need to be able to have a, on the user's prompt, variable that refers to the data set so that you can say dot filter, and produce a cut version of the data set and have that go out and come back. So actually, the compiler part of it is long since done. That was sometime in January. The distributed part is in progress. So that should be available on the time scale of probably a month or two, and to be able to point to their own collection of root files and say that those are that's the input data set. Now let me define new data sets based on that and perform histogramming based on that within, like I said, 1 or 2 months from now. And then enclosing that in some higher level query server would be beyond that.
Okay, thanks. I have another question, but I'll ask you after everyone else signs off like this.
Okay.
And Jim, since you mentioned this in the talk, am I getting right that writing the schema for the customized C++ class, I'll be able to read any root structure?
Mm-hmm. Yeah, put an asterisk next to any. Yes.
Well, but that actually
asterisk?
implies if I can write the code parser over the custom classes, then it means that we can read any, any, whatever, put it in quotes or whatever,
yeah.
Any root structure. It's only question of writing a schema. That's my question.
Yeah, it's actually not that complicated. So the starting point is not the C++ class. The starting point is the root file, which encodes all the information we need to know about the C++ class. Data members, not the methods. So the asterisk next to any is whether or not uproot can read it. So if the class is fully split down to primitive data types, then yes, uproot can read it. It can get them into NumPy arrays. It can infer a schema over it. It might not be the schema that you want, but then you can tweak that schema that it produces. Usually the problem is the names are misleading. And for some well-known data types like CMS Nano AOD, a lot of people use the same structure, so we can have an already existing function for that to convert all the names into reasonable names.
Well, so what would be the correct approach? So you already mentioned it starting from the root rather than C++, but addressing the generic use case, knowing that the root contains the custom classes,
mm-hmm.
where, it would be your advice to start with?
So if you're starting with a root file that has custom classes in it, we can infer a schema from the branch structure of the nested branches in the root file. and the leaves that describe the data types. So we can infer a schema from that. I mean, there's, depending on whether you're happy with the names that it gives you, there might be nothing to do after that.
Okay. Okay, thanks.
Yeah. Okay. Yeah, the problem with the names is that you get things where if you do automatic conversions, you get something which is like a list of muon objects, and its name is number of muons because of the way that branches work. So we would have a custom name conversion for CMS Nano AOD, and if you have another different class than that, you probably want to write your own name translation. Other questions? Because we are now half an hour over. So if that's it, thank you everybody for coming.